Hello, my BC Calculus kids. We're looking at section 15.5 on LaGrange error bound is what this one's all about for Taylor polynomials. So when a Taylor polynomial is used to approximate a function, we need a way to see how accurately the polynomial approximates the function. How much the approximation is off by is referred to as the remainder or the error of the polynomial. So in general, you've got the function equals, and this is kind of like when you think about long division with polynomials. The function equals whatever the polynomial approximation is, which in our case is a Taylor polynomial, plus the remainder, whatever the remainder is. If I take this and solve for the remainder, then the remainder is equal to whatever the function was minus the polynomial approximation. So here are, mathematically speaking, what these inequalities would be, what these error bounds would be. And so you have the equations here, but it's probably easier for you to recognize it or see it when you see it in action in an actual problem. So we're going to not spend too much time on the theorem behind it. We're going to spend more time on the application of it. But you can, after you get the hang of it and you go back and look at these, it'll make a whole lot more sense. So I'd like for you to just hold on to all these boxes, and we might come back and look at them later. And I think that's it for the front page. All right, page 2. That was quick. So, example 1. Let f be a function with 5 derivatives on the interval from 2 to 3. Assume that the 5th derivative, the absolute value of it, is less than or equal to 0.2. for all x in the interval from 2 to 3, and that a 4th degree Taylor polynomial for f at c equals 2 is used to estimate f of 3. All right, what does all that mean? And you're like, I don't know. How accurate is the approximation, and give 3 decimal places? Well, this is the approximation right here, because that's got the inequality thing with it. That's where your error is looking at. They're looking at this. So if I take the 5th derivative, think about what a Taylor polynomial would look like for the 5th derivative. It would be the absolute value of that 5th derivative over 5 factorial, and then since it's centered at 2, then I have a grouping that's x minus 2 to the 5th power. Right? So what we're looking at is they want to know, I know that I have the 5th derivative is less than or equal to 0.2. So that's the maximum it can be. If you look back on the front page, it has a capital M in the location where this is. So I know that 0.2 is the biggest that it can be. That's my f to the 5th of x, and that's coming from here. Over 5 factorial. And I want to estimate what it is at 3. So my x is 3. So I've got 3 minus 2 to the 5th power. I'm going to put an arrow on here. And so that's what I'm actually calculating out. This 5 factorial is really 120. If I take 0.2 divided by 120, 3 minus 2 is 1, 1 to the 5th. I end up getting, and you can put this in the calculator and check it out, 0.00167, which we're going to use 0.002, just rounding it to 0.002. So the error, you just found the error. What you did just in that step is figured out the error. How accurate? In other words, what's the error in this approximation? And so that's the way that you're going to find the error. And in our case, the error has to be less than or equal to 0.002. So you take that 5th derivative, the 5th term, 5th powered term, and you create your Taylor polynomial from that, and then calculate it out. All right, so then it says, suppose that P4 in a polynomial of 4th degree at 3, you get an answer of 1.763. Use your answer in part A to find the interval in which f of 3 must reside. And so what you do is f of 3, you create this inequality. And f of 3 is where you're starting from. And you know that at f of 3, it is, or it's approximated to be, 1.763. Now you notice I'm leaving a space. And I'm going to make an inequality over here, 1.763. So think about it. If you're allowed to be at 1.763 and your error is 0.002, then from 1.763 I can go left by 0.002 and I can go right by 0.002. If I go left by 0.002, then I'm subtracting it from that. That was my blank. If I go right, I'm adding it to it. So I'm going to take 0.002 and subtract it on the left, add it on the right. That's going to be my interval for which I can have values. So if I look at it, it's going to be 1.761. Again, use your calculator. You can check me out, make sure I'm right. And on the right, it's going to be 1.765. Okay. So then the question is, this is a popular question on the exam. Could f of 3 be 1.778? Why or why not? And could 1.764 be an answer? Why or why not? So there's two parts to this guy. First part is this. You're looking at 1.778. Is 1.778 between here? And the answer is no. 1.778 is outside the interval of error. There's a few different ways you could say that, but that'll work. How about 1.764? Is that between these two? And the answer is yes. And why or why not? Because 1.764 is within the bounds of error. Okay. That's it, example 1. We've got 5 examples, so 1 down. The next one, they say, the function f has derivatives of all orders for all real numbers x. Assume that f of 2 is 6, f prime of 2 is 4, f double prime is -7, and f triple prime is 8. Right, third order, third degree, Taylor polynomial for f about x equals 2, and then use it to approximate 2.3. Now we've done this before. This is kind of an old question from a previous section, but we're going to use it to answer questions that are about this error. That's the big topic for this section. So P3 of x equals, they tell me the first term is 6, so there you go, 6 plus. They tell me the second term's coefficient is 4. Finish the Taylor polynomial. Over 1 factorial, this one's centered at 2, x minus 2. Get to the next one. The next one is a -7. So maybe I'll change this from a plus to a -7. Over 2 factorial, x minus 2 quantity squared. And then a plus 8 from here over 3 factorial times x minus 2 to the third. Did we get a third degree polynomial? We did. Okay. So can I make this better? Because eventually I'm going to have to evaluate it for 2.3. So let me do that. See if I can pretty it up just a bit. It's going to be 6 plus, well, 1 factorial is 1, so this is 4 times x minus 2. The next one is 7 over 2, 2 factorial, 2 times 1, so 7 over 2, x minus 2 quantity squared. And this one would be 8 over 6. 3 times 2 times 1 is 6. So 8 over 6, that's like 4/3. I shouldn't have written so big, because now I need to know what it is at P sub 3 of 2.3. Well, think about your parentheses. I'm going to change my color for just a second. Think about your parentheses. Each of your sets of parentheses is going to be 2.3 minus 2, or 0.3 in the end. So each of your sets of parentheses is going to turn into a 0.3. So that's going to be, if I arrow this off, it's going to be 6 plus 4 times 0.3 minus 7/2 times 0.3 squared plus 4/3 times 0.3 cubed. And that's going to give you an answer of approximately, I should use squigglies, 6.921. And again, grab your calculator and you can make sure that that's accurate. So here comes the section 15.5 stuff, the error bound stuff. The fourth derivative of f satisfies this inequality where it's less than 9. For all x in the closed interval from 2 to 2.3, use the LaGrange error bound on the approximation of f of 2.3 found in part A to find an interval from A to B such that f of 2.3 is between it. So kind of what we're doing is what we did up here, where our final answer is going to be this type of a thing. We just have to derive what it is. All right, so let's think about it for a minute. The error, they're telling me right here, this is my error formula. So in other words, I am looking at a fourth derivative, a fourth degree Taylor polynomial that would look like this. The error, it's going to be f4 of x. I'm going to write out the official formula and then we'll fill in the pieces we know. And this one is centered at 2. So that's what the error would look like, just like it did back in part A of example 1. So the question is, what is this fourth term? And if I were to go to the fourth term for this, it is this value. Just like back in example number 1a, I go to the inequality and the numerator is coming from what that inequality can max out at. This one maxes out at 9, right? Because that's what my inequality is now. So this piece here is 9, the top. 4 factorial, 4 times 3 times 2 times 1 is 24. And then I have 2.3 minus 2 to the 4th power, because they wanted to know what it is for that approximation at 2.3. So when I go to my calculator and calculate this, I get 0.003. That's what my error is. So the error, and I'll write this like we did up above, so the error has to be within 0.003. Well, we said that the answer was 6.921. So I can go 0.003 to the left and I can go 0.003 to the right, and that's going to be my interval for where this value for 2.3 actually exists. So on the left I'm doing 6.921 minus 0.003. Sneak a little less than in there. And on the right I'm doing 6.921 plus 0.003 in order to get my actual interval, and that's going to be 6.918 is less than or equal to f of 3. f of 2.3 is less than or equal to, added on, 6.924. All right, so we got it. That's our interval. And then the last one is, based on this information, could f of 2.3 equal 6.992? Check out your interval. Is it within your interval? And it is not. And so your answer is nope, can't happen. It's not within the bounds of error. All right, example 2 done. We are working on example 3. They're bringing in things from other sections to be able to answer these. And these, by the way, are typical AP type questions, things you might see on the exam where you have all these multi-parts going on and you're doing all sorts of different things. So this one says, this one's going to bring back some things we learned from the last section, but it's also going to then ask us about the error in part D, which brings us to the new section. So I'm looking at this sine of x squared. Let f of x be sine of x squared plus cosine of x. The graph of the absolute value of the fifth derivative is shown below. Write the first 4 non-zero terms of the Taylor series for sine of x about x equals 0, and write the first 4 non-zero terms of the Taylor series sine of x squared about x equals 0. So here it goes from the last section. We know, remember those? We know that the sine of x equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, the first 4 terms. They want me to say, okay, well now what is it for the sine of x squared? I think we kind of liked these the other day when we were doing them. If I replace each of the x's with an x squared, and we did this, I know this came up in class with one of the examples from the last section. Anyway, you're replacing, so now it's an x squared. This one's going to be x squared cubed. That's x to the 6th over 3 factorial. X squared to the 5th, x to the 10th over 5 factorial. Minus x squared to the 7th, that would be to the 14th over 7 factorial. All right, we covered both of those bases. That's part A. Part B, write the first 4 non-zero terms of the Taylor series for the cosine of x about x equals 0, and use the series for the sine of x squared found in part A to write the first 4 non-zero terms of the Taylor series for f. Well, remember, f wanted us to add these things together. I want the x squared, sine of x squared, and I want to add it with the cosine of x. So I'm going to add those terms together. But the first thing I've got to do is write down what the cosine of x is. So cosine of x equals 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And again, you're supposed to have them committed to memory there. So my function says f of x, what I'm looking for, and that is the sine of x squared plus the cosine of x. So what I have to do, and I wrote a little note here on mine anyway, is that you're adding like powers. You can't combine them if they're not like powers. You can't add them up, which is what this is asking us to do. So that was my hint to myself on this when I was doing it. So I have a 1. Do I have any other constants? No, nobody's just got a 1. So 1 is one of my first ones. All right. The next thing I have, and remember I'm adding this sine of x squared with the cosine of x. The next thing I do have an x squared, right? I have an x squared that has to be added with x squared over 2 factorial. But this is negative. This guy's positive. So positive, negative, x squared over 2 factorial. Now we'll come back and do the math of that in just a minute. Next one, I'm going to start with a plus because that's what they normally, I'm trying to add them up. I have an x to the 6th, but I also have an x to the 4th, but I only have a singleton of that. So he doesn't have any partner to be added with. But I do have partners on the 6th powered guys. I have a negative x to the 6th over 3 factorial, and I have a negative x to the 6th over 6 factorial. There are 4 terms. That's what we want, the first 4 non-zero terms, 1, 2, 3, and 4. It's just now a matter of combining them, turning them into one term, like the ones that you can actually add together. So I'm going to put a little equal here. We have a 1 plus. Now don't get too crazy with this. This is 2. 2 times 1 is 2, so this is a half. If I have 1x squared and I take a half away, I'm left with a half. And so my first term is going to be x squared over 2, or 2 factorial, one and the same thing. Third term, I don't have anybody to add with, so plus x to the 4th over 4 factorial. And this last guy, he's a little bit of a humdinger there because I need like denominators. This is a denominator, I'll put it down below. This is a denominator of 6. This is a denominator of 720. All right, so off to the side, what I'm going to do is come up with common denominators of 720. So this is a negative something over 720 minus something else over 720. Well, if I divide 6 into 720, it goes 120 times. This is x to the 6, by the way. This one is already the 720, so minus x to the 6th. If I combine them together, negative 120 and negative 1 give me negative 121, x to the 6th over 720. Can you still see me? No. I went off the page. So I just did off to the side, combining these, adding two fractions together. So this is going to be a minus 121 x to the 6th over 6 factorial, or 720. You can write it either way. They're one and the same thing. And you have just added, to get f of x, the sine of x squared plus the cosine of x. And there it is. Find the value of, for part C, f to the 6th derivative at 0. So if I'm looking at this, remember what that means. This means it's the 6th derivative. Well, in our case for these Taylor polynomials, which of these choices is my 6th derivative? And it's the one with the 6th power. So 6th derivative means the one with the 6th power. And the guy with the 6th power is negative 121 over 720 x to the 6th. Now go back and think about in previous questions what this fraction actually means, right? What this fraction actually means, if I go back and flip over to, like this guy at the bottom. That turned out to be this numerator right here. And so if we want to know f to the 6th of x, it's whatever that numerator is. And so if I flip back to where I'm at, I know that f to the 6th of 0 equals negative 121. By the way, just for point of conversation, the book has this as a positive 121, but I don't see how that fits, so I'm going with negative. But just if you have an idea as to why they might have, I mean, they can always make mistakes, but I chalked this one up to be their mistake and not ours. So just throwing it out there in case you do have a thought on that. All right, here comes part D. Part D says, let p of x, a polynomial of 4th degree, for f about x equals 0. We already did that. We did the polynomial. Using the information from the graph, now we're coming to the graph up there, of the 5th derivative, absolute value, shown above, showed that p of 4, when you put a 1/4 into the Taylor polynomial and put a 1/4 into the regular function and subtract them, that it's going to be less than 1 over 3,000. Now this is another way of writing error. Not that we're going to use it that way, we're going to use it this way. This is going to be how we're going to calculate the error, which is what they're asking about. But this is an alternate form for you to be able to show the error. When you take the polynomial minus the actual function value and subtract them, that gives you a remainder, and that remainder is the error, which is what we talked about at the very, very, very beginning. All right, so this one, I'm looking at finding the error, and error is, I'll put it this way so you can see it, error is less than or equal to, in our case we want the 5th powered polynomial, absolute value, over 5 factorial times, it's centered at 0, so it's just x to the 5th. Okay, so if I go to the 5th powered for this guy, I don't have that, right? My polynomial that I've generated is all even powers. It's 2, 4, 6, yada, yada. I have to go to the graph to be able to get what this number is. So I'm going to go to the graph. Let me pull this down. And what you really need to do, because it's almost caught me when I was doing this, is you need to make sure you're watching the scale of the graph. I thought originally that this was 1, but it's not. 1's way over here. And the x value that I'm concerned about, let me go back and show you the bottom, and then we'll flip back to the top again. The x value I'm concerned about, my x value, maybe I'll put it in a different color, my x is equal to 1/4. That's what the x value is. So I'm looking at, what is my graph? What is x at 1/4? I want to know what that y coordinate is, because that y coordinate is this piece. So I want to know what happens when x is 1/4. If I go back up to the picture, Again, this is 1 over here, so 1/4 would be this dot right there. And I estimated, because that's what you have to do with this, I estimated this coordinate to be 1/4, comma 38. And you could estimate it a little off from that, but that's the general idea. So 38 was what I chose. It's just shy of 40. And let me go back down here. That is this value right here. So I'm using 38. So my error, and you can use the absolute values, I guess, to be perfect, but is 38 over 5 factorial. Well, 5 times 4 times 3 times 2 times 1 is 120. We said our x is 1/4 to the 5th power. And then I go to my handy dandy calculator and I say, all right, Mr. Calculator, what is that? So my error has to be less than or equal to, and when I divide this, I get 0.00031. And I have to show that it's less than 1 over 3,000. Well, 1 over 3,000, I'm going to show you this way. My error, and you can keep, I guess, keep the absolute value since we started with it, is less than 0.00031, which is less than 1 over 3,000, which is actually, if I were to divide that out, 0.00033 repeating. So is this less than that? And sure it is. Not by a whole lot, right? By what, a 10,000th or so? But yes, it is definitely less than that 1 over 3,000 that you were trying to show. So there you go. That, my friends, is example 3. Got 2 to go. All right, here's the next guy. And again, they're going to have us start with things from other sections and move on to things from this section as we go. So the first one is we want to write the 4th degree Taylor polynomial for f about x equals 3. So they tell you you've got a Taylor series. It converges for all x on the interval f to the 4th. It's not f to the 4th, but 4th derivative of f is less than the 4th derivative at 3 for all x over the interval from 3 to 4. The nth derivative of x of the function at x equals 3 is given here. What on earth is all this? All right, so the first thing we want to do is we want to generate our Taylor polynomial from this. Now, this right here, and it's centered around x equals 3. So this right here, what they gave you is f of 3. In other words, this is your first term, right, in your Taylor polynomial. So they gave you the first term already, and we've got to come up with the rest of them, and we want a 4th degree. So my polynomial, well, let's go over to the side here, right? On the side, we've got to figure out to the 4th power, or 4th derivative, what this thing is going to be. So f prime of 3, first derivative, equals. How am I supposed to get that? And so if I go back up here, isn't this how I'm going to generate these powers? So if I have the first derivative at 3, which I'm trying to do, then it's going to be an n of 1. All of my n's become 1s. So let's see what that looks like and see if I can then come up with an answer for this, an actual number answer. -1 to the first times 1 factorial over 5 to the first and 1 plus 3. Okay, go through the whole deal there, and I solve that out, and that becomes a -1 over 20. Then I'm going for the second derivative. I'm going to do the same exact thing, but now all of my n's become 2. So I have -1 to the second, I have a 2 factorial, I have a 5 to the second, and I have a 2 plus 3. Well, generate that, and that comes out to equal 2 over 125. I have to go to the 4th degree, so I've got to go a couple more places here. So third derivative is going to be -1 to the third, 3 factorial up top, 5 cubed, and 3 plus 3. on the bottom. That comes out to be negative 6 over 750. If I go to the fourth, I guess I could do the 4 ticks there. I could just write the 4. I'm talking 4 and should be writing a 3. There it is. If I plug the 4 in, you know where it's going. Negative 1 to the 4th, 4 factorial over 5 to the 4th, and 4 plus 3. That generates a term that is 24 over 4,375. All right, now you're ready to generate the polynomial. So here it goes for this guy. This is my polynomial of 4th degree has a first term of 1/3. Minus, because it's a negative 1 over 20. So I've got negative 1 over 20 over 1 factorial. Don't forget you still have to put them over their factorials, times my centered group, which is at 3, so x minus 3. Next one is 2 over 125, so plus 2 over 125, but that's with my 2 factorial and a grouping of x minus 3 squared. All right, next one is negative, so minus 6 over 750 over 3 factorial x minus 3 cubed. And the last one is this 24 guy, so he's going to be a positive, and 24 over 4375 over 4 factorial times x minus 3 to the 4th power. Kind of went off the page there a little bit. There you go. What the heck am I going to do with that? That is really a hot mess. So I can't have these complex fractions within fractions. I need to kind of work my way through that. So let me see if I can prettify it a bit. 4, right? We're a polynomial of 4th degree. 4x equals 1/3. Anything over 1 is just itself. So the next term is 1 over 20. Times x minus 3. Now, I'm going to change my color and maybe go up above and talk about this guy. If I have 2 over 125 and I am dividing it by 2 factorial, dividing by 2. Really what I'm going to do then is take 2 over 125 times 1 over 2, and my 2's cancel. So that coefficient becomes a 1 over 125. That's what's coming next. That's this. So 1 over 125, and that's going to be an x minus 3 squared. You're going to do the exact same thing with each of these next terms. So really what I did over here, what I did was I multiplied by 1/2. In this one, I'm going to multiply by 1 over 3 factorial. Well, that's 1 over 3 times 2, or 1 over 6. When I do that, the 6's cancel. So look at what that coefficient's actually going to be. It is a minus 1 over 750 times x minus 3 cubed. If I have 4 factorial, guess what that is? It's 1/24, which then cancels with the 24 numerator, and I get 1 over 4375, and that would be x minus 3 to the 4th power. So it actually worked out relatively nicely in the midst. But a little bit of algebra going on in that thing. All right, find the radius of convergence for the Taylor series for f about x equals 3. Well, you need to figure out what the Taylor series actually is, and so I'm looking at right here. It's going to be easy. Okay. If I look at, here's what my term is for this guy. And I'm sorry for the pause, but here's what I'm looking at. I know that f to the n of 3 over an n factorial times x minus 3 to the nth power is what my radius of convergence is, what I'm looking at for this particular function. So if I put in the pieces, f to the n over 3, this piece here, f to the n, it's the whatever nth derivative at 3, that's the same thing I have, and yes, you can still see it on the screen. It is this guy. So what I need to do is figure out, remember you're using like the nth term for this thing? You want to know what the nth term would be. So here I go. I'm going to replace f to the n over 3, the nth derivative of 3, with this. So my pink guys get replaced. So I'm going to have negative 1 to the n times n factorial over 5 to the n and then n plus 3. But I still have the rest of this. This is over n factorial and then times x minus 3 to the nth power. Now, since I'm trying to find a radius of convergence, I'm eventually going to ratio test this thing, but I'm trying to get it into a form that I can actually use. So that's why I'm looking for this nth term there for this. So I have this, let's see, this would be the same thing as negative 1 to the nth times n factorial over 5 to the n times n plus 3 divided by, in other words, times 1 over n factorial, and then times x minus 3 to the n. Is that all the pieces? Here's the numerator divided by numerator. Okay. Does anything cancel? Is really the idea. And we do. We've got a couple things going on. These n factorials can go. And so I guess the best road I've got for this thing is a negative 1 to the n times x minus 3 to the n over, and then I have 5 to the n, and I have an n plus 3. That hole punch got in my way. Now I need to ratio test. So now I have that nth term. So I'm going to ratio test this thing like we do in order to be able to figure out what the radius of convergence is. Now if you remember the ratio test, it's the limit as n approaches infinity for the n plus 1 term. Well, what would the n, it's the absolute value, n plus 1 term, I don't care again about this negative 1 because it's an absolute value, so I can ignore this beginning. But I am concerned about this. So I'd have x minus 3 to the n plus 1 power over 5 to the n plus 1 power. And then, remember this is n plus 1. N plus 1 plus 3 gives me n plus 4. So there's where the n plus 1 term would be. But I need to then multiply that by the reciprocal of the original function. Well, that would be, now I'm going to flip my original guy, which is this guy over here. So I'm going to have a 5 to the n up top. I'm going to have an n plus 3. I'm going to have a x minus 3 to the nth power on the bottom. And my job is to try to simplify that out. All right, so here I go, limit as n approaches infinity. Let's go with the x minus 3's. Where's the bigger x minus 3? It's up top, so I have an x minus 3. 5's, I have a bigger 5 on the bottom. Left with a 5 there. And then technically I have an n plus 3 over an n plus 4. But when you let n equal infinity, this is just, it zeroes out. It gets canceled and becomes a 1. So I'm left with an answer of the absolute value of x minus 3 over 5. Now what does that have to stay between in your radius of convergence? And it has to be less than 1. I think it was just less than. Is it less than or equal to? Oh, we don't know. Yeah, it's just less than. Okay, so here we go. We're going to take that thing and make it going to take this inequality and turn it into the triple guy. So it's less than x minus 3 over 5 is less than 1. Remember, it has to stay between there. And then you're solving for x. So both sides get multiplied by a 5. Negative 5 is less than x minus 3 is less than positive 5. Add 3 on to both sides. Negative 2 is less than x is less than 8 when I add that 3 on. So what is your radius of conversion between negative 2 and 8 is a distance of 10. If I take half of that, it is 5. And there's your final answer. That one took a lot of doing. I think that beginning step here of remembering that you got to do that, get it simplified into its nth term before you actually do the ratio test is probably the hardest part of that guy. All right, C. Show that the third degree Taylor polynomial approximates f of 4 within an error less than 1 over 4,000. So I'm really looking for the fourth derivative at 3. It's a third degree that they're looking for. In order to approximate the error, you have to go one more past that. So what you're looking for is the next term. Remember, we saw that in other parts too, that it's the next term. So it will be the fourth power for this thing. Well, what do we know f of 4 at 3 is? And if I go way back, here's what let me put the formula together for where this is going to be for the error. And then I'll tell you where you're getting the numbers from. The error we know has to be less than or equal to, and it's the fourth derivative of x over 4 factorial times the group x minus 3, centered at 3, to the fourth power. So maybe I'll even take this piece away so it doesn't get confusing in the midst. We're looking for what it is at 3. My f to the fourth degree at 3. Maybe I can put the 3 in here for my x, and well, no, I'll leave it there. That's fine, x. If I go back up to my very beginning, what's the fourth powered coefficient? That's what you're looking for. So if 24 over 4375 is your numerator as you're doing this error problem. So you know that the error, such a weird word, error, is less than or equal to 24 over 4375 over 4 factorial times 4 minus 3, because I'm trying to approximate what it is at 4. Equals. Well, just like before in those problems I showed you back in part A, if I'm dividing by this factorial, I'm really multiplying by 1 over it, and 4 times 3 times 2 times 1 happens to be 24. So really this is what I'm multiplying by, which cancels my 24s, so I get 24 over, oh, by the way, this is to the fourth power, 24 over 4375 times 1, 4 minus 3 is 1, 1 to the fourth is 1. And so then the question is, well, what the heck is, wait a minute, this was 1, the 24 is canceled. So I have 1 over 4375. Is that less than 1 over 4,000? And the answer is yes, because it's a bigger denominator, smaller number. That takes care of example number 5. We are on to 6, the last one, and it uses a table, which makes it different than what the other ones have been. They've been giving us formulas for all the rest of these. So example 5, I might have lied. I think there might be 6 examples. No, 5, this is it. Okay, I know this is a long one. Let h be the function having derivatives of orders. Look, we've got all these different derivatives given at different places, at different x values. Selected values of h and its first 4 derivatives are indicated on the table to the right. The function h has these 4 derivatives increasing over the interval from 1 to 3. Write the first degree Taylor polynomial for h about x equals 2 and use it to approximate 1.9. Is the approximation greater than or less than the h of 1.9? Explain your reasoning. Now this brings up some stuff from back in Calc AB, the ending of it anyway, about it being an overestimate or underestimate. So I want a first degree, P1, a first degree polynomial. about x equals 2, right? So if I think about what this is, as far as these Taylor series go, the first term is going to be whatever h of 2, they're calling it h. Normally it would be f of whatever it is, but this one's being called h. So it's whatever the first y value is, plus the first derivative at 2, and then times the center of x minus 2. So I'm going to go to the chart, and I'm going to figure out from the chart what that is. H of 2 is 80. H prime of 2 is 128. And then my x that I'm looking for is 1.9. Well, actually, yeah. Well, let me leave it as an x for now, because we'll do it as a separate step when we evaluate. So then it's just times x minus 2. There's your first degree polynomial for this particular situation. Then they want us to approximate it at 1.9. So plug a 1.9 in for your x. 80 plus 128 times 1.9 minus 2, and that actually gives you a value of 67.2. And then it says, this is the part that's kind of an A-B thing, is the approximation greater than or less than the actual value of h of 1.9? Well, we have no idea what h of 1.9 is. We had estimated it to be about 67.2, but the question is asking, is it an overestimate or underestimate? That comes from second derivatives, and if the function is concave up or concave down. So I want to check the concavity of this. I'm asking myself, what's the concavity of this guy? Because, let me go over here to the margin. If it's concave up, then it's going to be an underestimate because all of my tangent lines are below. If it's concave down, my tangent lines are all above it. That's going to be an overestimate. So I'm looking for which way it goes. That's my idea. So I go to the second derivative at 2. Second derivative, so I'm looking at h double prime at 2. Is it concave up or concave down? It's 488 over 3, which is positive, which means it's concave up. If it's concave up, it's going to be an underestimate because your tangent lines are below. So, concave up, underestimate. Now, I think Mr. AP accepts the fact that it's just saying that it's concave up means that it's going to be an underestimate. You could add on that the tangent lines are below because tangent lines or derivatives, however you want to say that, are below. Okay. That takes care of part A. Part B. Write the third degree polynomial for h about x equals 2 and use it to approximate the 1.9 again. So in other words, we're going to take a few more terms to this thing. So let's see if we can generate some more terms. We know what the first couple are. I know that, and I'm looking for a third degree. So I know it goes 80 plus 128 x minus 2. Now the next term would come from, this was the first derivative when I did it. Now I want the second derivative. The second derivative at 2 is your 488 over 3. But that's over 2 factorial. I didn't need that one here. It was over 1 factorial. But this one's over 2 factorial. And I have my group, x minus 2, that's now being squared. We'll have to go third degree, right? So I go to the next term. That's 584 over 9 over 3 factorial x minus 2 to the third. And so I'm going to do the same type of thing that I did back on those other problems. I'm going to multiply this guy by 1/2, this guy by 1/6, and here's what happens, just for the sake of time. You can use your calculator and check me out. 80 plus 128 times x minus 2 plus, if I do the math here, it's 488 over 6 multiplying by 1/2. This one I'm multiplying by 1/6. So this one, let me finish this out. And the last one is going to be 4, is it 448 or 5? Actually, this guy, I took the wrong one, didn't I? The next one over would be 448. Did you catch that? Means that this guy's a 448 over 9 times 6. Well, this was a 3. That's what it is. I'm like looking at my work saying, wait a minute. 448 over 3. That generates 3 times 6. 3 factorial is 6. 3 times 6 is 18. Ooh, that was rough for me. Then they want me to use that to generate what it's going to be for 1.9. They want me to estimate P of 3 of 1.9. So now I'm going to take and put 1.9 into all these things, calculate it out. Comes out to be about 67.988. So when we did a first degree polynomial, we got 67.2. When we do a third degree, we get 67.988. Which one do you think is more accurate? A lot like the idea of integration. When you put in, the more rectangles you put in, the more accurate your area is going to be. Same with this. The more terms you take, the more accurate your answer is going to be. So the better answer, this guy's the closer guy. And actually it fits with what we were saying here. Is it an underestimate or an overestimate? And we said it's an underestimate, and sure enough it is. It's a smaller number than what we actually got for the next round. If I were to take more and more polynomial terms, I'd get an even more accurate answer. Last piece. Use LaGrange error bound to show that the third degree polynomial for h about x equals 2 approximate 1.9 with error less than 3 times 0.0004. Well, what does that look like? That is 0.0003. 4 decimal places, right? This was a third degree. The polynomial we just took is the third degree, and you have to, in order to find the error, use the next term, right? We said that before. So I want to take the next term. I'm going to set it up the long way with the formula just so I can fill in pieces and it makes sense to me. So if I want the next term, third degree, I'm going fourth degree, it looks like this. Well, the fourth degree at 2, the fourth derivative at 2, that's my 584 over 9 that I was trying to use before. 584 over 9 over 4 factorial times 1.9 minus 2 to the 4th power. All right, so you grab your handy-dandy calculator and you calculate all that out. It comes out to be 0.00027. And that is less than 0.0003. And so you have just shown the error for that one. And that takes care of section 15.5 and unit 15. Bring me your questions to class, and I will see you soon. Bye.